Alright, let's start with the next video. The next question is, state and prove the following properties of Laplace transform. The first one is time domain differentiation. Okay, let's start with the first one, time domain differentiation. And what is actually time domain differentiation? The Laplace transform of d by dt of x of t will be equal to s into x of s minus x of 0, provided if the Laplace transform of x of t is equal to x of s, then Laplace transform of d by dt of x of t will be equal to s into x of s minus x of 0. That's what we need to prove. Okay, so what is the actual expression for Laplace transform? So L of x of t is equal to x of s is equal to actually integral, if it is a unilateral Laplace transform, it is 0 to infinity x of t into e raised to minus st dt. Okay, therefore let me get straight away into the proof. Therefore Laplace transform of d by dt of x of t is equal to, here you have to take care that L of x of t means integral x of t into e raised to minus st. So L of d by dt of x of t will be equal to integral 0 to infinity d by dt x of t into e raised to minus st dt. Now you need to elaborate this integral. Before that, let me like this. I'm taking u is equal to this function e raised to minus st, and v is equal to x of t. Okay, I'm taking u as e raised to minus st and v as the signal x of t. Now listen very carefully. Now what is integral u dv? You have to apply the product rule of integration, right? That will be equal to u into integral of dv, right? That is integral of dv is, okay, I'm writing integral of dv minus integral of du into v, right? This is the product rule of integration. Okay, so what happens is integral u dv or integral u dv becomes u into integral of dv is v itself, right? uv minus integral du into v. Okay, right. So this is equal to now what is du? U equal to e raised to minus st. Therefore I can write du is equal to differentiating e raised to minus t with respect to t, you will get minus s into e raised to minus st. Okay, so this integral becomes integral u dv, that means e raised to minus st into dv equal to d by dt of x of t is equal to u into v. First term is u into v. U into v means just e raised to minus st into x of t. Okay, okay, e raised to minus st into x of t minus integral of du into v. Du means it is minus s into e raised to minus st into v. V is x of t. Okay, dt. I can simplify it as e raised to minus st into x of t plus s as a constant with respect to time differentiation. So plus s into integral e raised to minus st into x of t dt. Okay, therefore now let us come back to this expression. So what we have in our left hand side here is this thing, right? Just we didn't put on the limits, that's all. Okay, so this is equal to its solution is given by this expression but only with limit. Okay, so under the limits e raised to minus st into x of t plus s into integral x of t, I can write it as x of t e raised to minus st dt. Okay, the limits will be 0 to infinity. Now let us put on the limits. That is equal to, while we put on the first limit, upper limit infinity, e raised to minus infinity becomes 0. Okay, so 0 minus, now let me put on the second limit, lower limit. So e raised to minus 0 into x of t becomes e raised to 0 is 1. So 1 into x of t will get x of t. So 0 minus x of t, actually it's not x of t, right? T is 0, right? So we have to put x of 0, right? X of 0. Okay, I think you're getting it. What I did is just putting 0 into this factor. So e raised to 0 into x of 0. Okay, plus s into, before putting on the limit into this expression, what is integral x of t e raised to minus st dt? It is nothing but x of s, right? X of s is integral x of t e raised to minus st dt. So I can write it x of s. Okay, so combining, this is L of d by dt of x of t, Laplace transform of derivative will give s into x of s minus x of 0. So we have got what we needed to prove. Okay, so hence the proof. Now let us prove the final value theorem of Laplace transform. What is final value theorem of Laplace transform? Final value theorem lets us obtain the final value of a signal. That means x of infinity, that is the final value of x of t at t equal to infinity, right? So x of infinity is limit s tends to 0 s into x of s. This is final value theorem, and we are going to prove the final value theorem. So how we start final value theorem is, you start with the time domain differentiation. We have just obtained the time domain differentiation, right? So we start with the equation. So again, taking unilateral Laplace transform, 0 to infinity d by dt of x of t into e raised to minus st dt. This is the definition for the Laplace transform of d by dt of x of t. Okay, L of d by dt of x of t. So that is equal to, we got it as s into x of s minus x of 0, just in the previous sub question. Okay, now what I'm going to do is, you have to observe that there's a limit s tends to 0 in the RHS. So I am putting limit s tends to 0 on both LHS and RHS. Okay, so limit s tends to 0, integral 0 to infinity d by dt x of t e raised to minus st dt will be equal to limit s tends to 0 s into x of s minus x of 0. Okay, now what happens to the LHS if you put limit s tends to 0 in the LHS? There is only a single factor that contains s, and if you put s equal to 0 here, it is e raised to 0, that means that becomes 1. Okay, so that implies integral 0 to infinity d by dt x of t into 1 dt. Okay, that is equal to, what is limit s tends to 0 s into x of s? Limit s tends to 0 s into x of s. You might jump into the conclusion that it is 0, but it is not equal to 0. This is not equal to 0. Why? Because suppose x of s is equal to 1 by s. Let x of s is equal to 1 by s. Then limit s tends to 0 s into x of s is equal to limit s tends to 0 s into 1 by s, which is equal to limit s tends to 0 1 equal to 1 and not equal to 0. So unless and otherwise x of s is not clear, we cannot jump into the conclusion that this term is 0. So you cannot put 0 here. You write it as such. Limit s tends to 0 s into x of s. Okay, minus limit s tends to 0 x of 0. Limit s tends to 0, x of 0 is x of 0 itself. It's a constant value. Okay. Now, what is the LHS? LHS is derivative of x of t dt. Its integral. That becomes x of t itself. Okay. X of t. Right? It is the integral of derivative of x of t. That becomes the signal itself. But within the limits 0 to infinity. That is equal to limit s tends to 0, s into x of s, minus limit s tends to 0, x of 0 is x of 0 itself. There is no s term, no any variable. Okay. Now applying the limit, applying the upper limit, you will get x of infinity minus applying the lower limit, it is x of 0 equal to limit s tends to 0, s into x of s minus x of 0. You can cancel x of 0 and x of 0. And what you can obtain finally is x of infinity is equal to limit s tends to 0, s into x of s, and that is itself is the statement of final value theorem. So proved. Alright, the next question is find the inverse Fourier transform of the following signals. First question is 1 by j omega into j omega plus 1 plus 2 pi del of omega. Okay, these are very simple questions. So starting the question number A, before solving the question A, you need to take note of three things. First one is the Fourier transform of 1, signal 1 is 2 pi del of omega. It's an impulse function in the Fourier domain. Okay. The next is the Fourier transform of signum of t is 2 by j omega. We have already done this, and I think in video number 10, I think. Okay, so we have already seen this. The Fourier transform of signum of t is 2 by j omega. And the Fourier transform of e raised to minus at e of t is 1 by a plus j omega. That also we have seen several times, in fact. Okay, so if you are familiar with these three properties or these three relations, then this question is very simple. So question A says to find the inverse Fourier transform of the signal. Okay, this function. So I can address x of omega instead of small letter omega. The question is given in capital letter omega. That's the only difference. That's not a problem also. Okay, so x of omega is equal to 1 by j omega into j omega plus 1 plus 2 pi del of omega. Okay, the first term is given as a factor, right? So whenever you find a factorized form in the frequency domain, what you have to do is partial fraction. Okay, so this is a very simple partial fraction. I can I don't have to take a and b because it is very simple. So I can write it as 1 by j omega minus 1 by j omega plus 1. Okay, if you simplify it, you will get it 1 by j omega into j omega plus 1. So a and b are actually 1 and minus 1. If you want, you can take a and b, no problem. You will end up with the same result. Okay, plus 2 pi del of omega. Okay, so now take inverse Fourier transform because all these terms are known to us. Okay, so take inverse Fourier transform on both sides, and you will get x of t is equal to, what is the inverse Fourier transform of 1 by j omega? You know, signum of t, right? 2 by j omega is the Fourier transform of signum of t. Okay, so what will be 1 by j omega? 1 by j omega will be the Fourier transform of half signum of t. Alright, so 1 by j omega will be having an inverse Fourier transform of 1 by 2 signum of t. So 1 by 2 signum of t minus, next term is 1 by j omega plus 1. So what is the inverse Fourier transform of 1 by 1 plus j omega? It is e raised to minus t of t. Okay, instead of a, it is 1. So e raised to minus 1 t u of t. So e raised to minus t u of t plus what is the inverse Fourier transform of 2 pi del omega? We have already said 2 pi del of omega is the Fourier transform of 1. Okay, so here it is 1. So this is the final answer. Okay, let us continue with the question B. Question B is given frequency domain 2 pi del of omega plus pi del of omega minus something plus pi del of omega plus something. So this question is too much easier. All you need to know is the Fourier transform of 1 is 2 pi del of omega that we have already seen. Okay, then the next one you have to know is the frequency shift property of Fourier transform. What is frequency shift property of Fourier transform? If x of t is having a Fourier transform x of omega, then multiplying with the complex exponential e raised to j gamma t with x of t will give you a Fourier transform x of omega minus gamma. So there is a frequency shift here. Previously it was x of omega, now omega minus gamma, where gamma is the coefficient of j into t in this signal, a complex exponential signal being multiplied with x of t. Okay, this is frequency shift property. I can write it as frequency shift property. Okay, so with these two treasure in hand, we can solve the problem B. So the first term is before that let me start this way. 2 pi del of omega, we know it is 1. Okay, let it be there. Now you know the Fourier transform of 1 is 2 pi del of omega. Okay, so using with the help of frequency shift property, if I am writing e raised to j 4 pi into 1, what will be the Fourier transform? You can use frequency shift property, right? Because here the x of t is 1, which gives something x of omega here, and here this x of t is multiplied by e raised to j 4 pi t. Sorry, this e raised to j 4 pi t. Okay, so we are multiplying the signal 1 x of t with e raised to j 4 pi t, and according to this thing it should shift the frequency by 4 pi units. Okay, so 2 pi del of omega minus 4 pi. Okay, you have to take note of the sign of shift. Okay, here there is positive sign, here is to plus j 4 pi t, but here it is negative sign. Okay, now in a similar manner I can write e raised to minus j 4 pi t into 1 will be having a Fourier transform of 2 pi del of omega plus 4 pi. Good. Okay, so here it is also a frequency shift property. Here e raised to minus j 4 pi t is multiplied with 1, then the frequency shift will be plus omega plus 4 pi. Okay, now what I'm going to do is I'm just adding these two equations, this equation and this equation. I'm going to add them. So what happens is e raised to j 4 pi t plus e raised to minus j 4 pi t will give a Fourier transform. It is linearity, so we can add the transforms also. Okay, so what happens is 2 pi into del of omega minus 4 pi plus del of omega plus 4 pi. Okay, now what is the LHS? It is the magic expression in signal sense systems, right? You know, e raised to j theta is equal to cos theta plus j sin theta, and e raised to minus j theta is cos theta minus j sin theta, and when you add e raised to j theta plus e raised to minus j theta, you will end up in 2 cos theta. Okay, so our LHS is nothing but 2 cos 4 pi t, right? E raised to j theta, whatever be the coefficient of j is theta, so that is 2 cos theta. Okay, and so 2 cos 4 pi t will be having a Fourier transform of 2 pi del of omega minus 4 pi plus del of omega plus 4 pi. So we reached a very good relation. Now return to the question. What is in the question? the second and third term, pi into del of omega minus 4 pi plus pi into del of omega plus 4 pi. Did we get it? We have 2 pi into del of omega minus 4 pi plus 2 pi into del of omega plus 4 pi. So what is the inverse Fourier transform of pi into del of omega minus 4 pi plus pi into del of omega plus 4 pi? It will be cos 4 pi t. We can cancel these two. Okay, therefore inverse transform of 2 pi del of omega plus pi into del of omega minus 4 pi plus pi into del of omega plus 4 pi will be equal to, what is the inverse of 2 pi del of omega? That is 1. Okay, so I can write 1 plus, what is the inverse of this whole thing? That is obtained as cos 4 pi t. So 1 plus cos 4 pi t. It is the final answer. Okay, the next question is, obtain the Fourier series representation of the given waveform plot the magnitude spectrum. So normally when students see this type of question, they know how to do it. It is by using trigonometric Fourier series, right? Trigonometric Fourier representation. Normally I've seen students skipping this type of questions because this involves a large number of calculations. The calculations are simple, but it is tedious. Heavy integrals are there because a0 is equal to trigonometric Fourier series. Actually, trigonometric Fourier series represents x of t as a0 plus sigma n equal to 1 to infinity an cos n omega 0 t plus sigma n equal to 1 into infinity bn sin n omega 0 t. And what students find is, find a0 first, then an, then bn, and substitute in this equation, right? So what I have to say is, when students do this, there are many integrals because a0 is equal to, a0 is simple to find. A0 is 1 by time period integral over the time period x of t dt. You will get a0 very simply. But what about an? An is equal to 2 by t integral over a period x of t cos n omega 0 t dt. You find omega 0, substitute in it and get an answer. Bn is equal to, again, 2 by t integral over time period x of t sin n omega 0 t dt. So normally what happens is, these integrals are very tedious. They are simple, but they require a long time. Normally 15 minutes will be taken by an average student to evaluate all these integrals, and while doing so, there are so many chances to make errors while integration and putting the limits. Okay, so what students do is, they skip these questions because they require a large amount of time, and at the same time they may go wrong, they make errors. Okay, but what you will face is, or what you will get from this question is, a very simple method to solve this question. Very simple. While you had earlier taken 15 minutes average to solve this question, I promise you, you can do this question within 5 minutes or less than 5 minutes. That's a promise. All you need to know is some relations, some basics of signals. Okay, so be very attentive. I'm promising you, this is a very simple approach to do this type of problems. Okay, first find a0 of the signal. A0 is simple to find. Okay, so I'm taking a0's equation. A0 equal to 1 by time period integral over 1 time period x of t dt. Okay, what is time period? Time period is 0 to pi units. Okay, so t equal to pi units. Then what is x of t in this? T equal to pi units. What is x of t? X of t is, you know how to make the equation for x of t, right? It is a straight line. So slope into t plus intercept. Intercept is 0, right? 0. So slope is, what is the slope? Delta y by delta x. Delta y is a, delta x is pi. So delta y by delta x gives a by pi. So the expression is x of t equal to a by pi into t. If there was some intercept, plus that intercept also, but here is no intercept. Okay, so this is x of t. Now what is a0? A0 is equal to 1 by pi integral from 0 to pi. X of t is a by pi into t dt. That is 1 by pi square into a by pi square is also constant into integral 0 to pi t dt. That will give you a by pi square into t square by 2 from 0 to pi. That is equal to a by pi square into pi square by 2. That is a by 2. Okay, so a0 is equal to a by 2, and you might be intuitively knowing that a0 is nothing but the DC value of the signal. Okay, so I got a0. I'm keeping a0 as such. A0 is equal to a by 2. I'm preserving this equation. This is needed. Okay, now everything will be very simple. So now we are going into the simple steps to solve this problem. Before solving that, you need to take care of 2 or 3 points, simple basic points, like what is the integral of step signal. If you integrate step signal or constant signal, you will end up with ramp signal. Okay, I think you might be knowing this. So very simple basic points. If you know these points, you can do this problem by 2 minutes. So first one is integral of u of t, or step or constant signal, is a ramp signal. Okay, then you need to know about the differentiation property of Fourier series. What is differentiation property of Fourier series? If x of t is having a Fourier series coefficient Cn, then d by dt of x of t will be having Fourier series j n omega 0 into Cn. So this is very similar to Fourier transform property. So I think you might be knowing this also. And the last one more point you need to take care is the Fourier series of an impulse train. The Fourier series is it is 1 by ts. Okay, impulse train means we have already seen that these are impulse train. Okay, 0, this is a periodic signal, so we can take the Fourier transform. So I am giving p of t as the impulse train. Ts is the time period. Okay, then if you take the Fourier series of this periodic signal, you will get 1 by ts. Okay, p of k, or I can call it pk. Okay, or pn. We are giving n everywhere. Okay, pn. So pn is 1 by ts. This also you need to take care. I think I will prove it to you how p of t when taken Fourier series end up with 1 by ts. This is very simple. Okay, before that, can you suggest a mathematical expression for p of t? P of t in the sampling problems we have already seen it. Okay, p of t is equal to sigma over n equal to minus infinity to plus infinity del of t minus nts. Okay, we've already seen it. Okay, so its Fourier series coefficients will be 1 by ts. I will prove it. So what we are going to do is not a part of the problem we have to solve, but it gives an intuition. It gives this result. I think I can box this result also. So the Fourier series of impulse train is 1 by ts. Okay, then we are going to prove. If you want the proof, you can prove it. So I am drawing an impulse train. Zero, Ts is the time period. Okay, I'm giving it as P of t, naming it as P of t. Okay, so what is the expression for Fourier series? Pn is equal to, Pn is the Fourier series coefficients of P of t. Pn is equal to 1 by time period integral over 1 period. Okay, x of t into e raised to minus j n omega 0 t. Okay, this is the Fourier series coefficients. Now that implies Pn equal to 1 by t into what is the time period of P of t? Time period is Ts. So integral 0 to Ts. What is x of t? In one period, x of t is del of t. Okay, del of t into e raised to minus j n omega 0 t dt. And what is this integral? Using the properties of impulse function, you know, this will reduce to this del of t is existing only at t equal to 0. If you consider del of t alone, right, del of t alone, it is situated at t equal to 0. So what happens is this function reduces to its value at t equal to 0. You put t equal to 0 here. So e raised to minus j n omega 0 into 0 will give you 1. E raised to 0, 1. So integral 0 to t is del of t into 1. What is the area under an impulse signal? That is also 1. So you are going to end up at 1 by ts. Very simple. That's what I've already told you. 1 by ts is the Fourier series of impulse train. Okay. So for all n, we will get, I'm drawing Pn here for n omega 0. This is a frequency domain. Okay. So for all n omega 0, we will get 1 by t. This is not impulse. This is discrete amplitudes. 1 by t for 0, 1 omega 0, 2 omega 0, 3 omega 0, etc. Here also. Okay. So what I have done this much is nothing related to the answer, only a result. If you want to, if you are not to by heart, you can have this proof. Okay. Otherwise, just forget it. Okay, I have boxed all the important tips we needed to proceed to solving this problem very simply, very quickly. Okay, now listen very carefully. Okay, students, consider this signal. I'm considering a g of t signal, right, with a DC component A and some impulse component A del of t. Okay, right. My question is, the signal consists of both a DC, you can see this A, and impulse trains, inverted impulse trains, each of amplitude A. Now my question is, what happens if we integrate the signal? What happens when we integrate this signal? You know, integral of a step or integral of a constant is, step or constant is always giving you ramp, right? Ramp signal t. So what will be, I can prove that. If we integrate this step signal, right, this is a step signal or constant signal, you will get a ramp. Okay, so I am drawing this ramp, but when the ramp reaches here, what happens? It encounters a sudden minus a drop. Okay, so the value drops like this. Okay, but again the ramp is persisting there, so it again integrates, again an impulse comes, so the value drops, again integrates, drops, and it follows like this. Okay, so integrating this signal g of t will result in what? Results in a sawtooth wave, which is exactly similar to our question x of t, right? Okay, so what we have learned from this example, I can write it here. Integrating g of t, integral g of t signal will give you x of t, which is our question, or we can say g of t is equal to d by dt of x of t. Just reverse, if you differentiate x of t, you will end up in g of t also. Okay, so that is our master stroke. Okay, we are going to derive the results from this equation. I can box it. Okay. Alright, so what is g of t? How can you mathematically express g of t? G of t is nothing but the white colored signal, not the green one. Green one is x of t itself, right? Green signal is the sawtooth signal, which is same as our x of t. I'm asking about g of t. What is g of t? G of t, which is the white colored signal, is nothing but it has a DC signal, DC version A, minus what? Inverted del signals, right? It's not simply del of t, sorry, it is minus a into sigma n equal to minus infinity to plus infinity del of t minus n pi, right? T minus n pi. Here you can see each of the breaking in the ramp is occurring at pi, 2 pi, etc. So n pi. Okay, so this is the expression, mathematical expression for g of t. Now it's almost over. Answer is almost over. What we do is we assign, let me say, x of t is having Fourier series coefficient Cn, and this g of t will be having Fourier series coefficient Gn. Okay. Now from this expression, Gn will be equal to, okay, Gn will be equal to, using this property, it will be Jn omega 0 into Cn. Okay, right? But we need to find out Cn. Okay, the question is to find the Fourier series representation of x of t, Cn. Okay, that implies Cn is equal to 1 by Jn omega 0 into Gn. Is that right? So this is what we need to find out. So this is very simple. From this expression, we need to find out Gn. Once Gn is obtained, this equation will give you Cn. Okay, so what is Gn? Gn is equal to this DC term. This DC term will contribute A0, which we have already found out. A0 equal to A by 2. Now we can simply neglect this A, because we have already found out the DC component A0. Okay, so Gn is equal to minus A into sigma n equal to minus infinity infinity del of t minus n pi. Okay, so what is Gn is equal to Fourier transform of, or Fourier series of this thing. What is the Fourier series of this thing? Minus A into minus A is a constant. Minus A into, what you will get is minus A into 1 by ts, right? 1 by ts. Why? Because we have already derived it here, right? 1 by ts is the Fourier series representation of any impulse train. So this is nothing but an impulse train. Okay, so the Fourier series of impulse train is 1 by ts. There is a minus a scaled here, so minus a by ts is the Fourier series coefficient of this g of t, entire g of t. Okay, and what is ts here? Ts is actually 0 to pi, so pi. Okay, ts is equal to pi. That will give you Gn is equal to minus a by pi. Okay, so I think all of you are clear up to this. Now what I'm doing is, so we got Gn equal to minus a by pi. So what is this relation telling you? Therefore, the ultimate answer, final answer, Cn is equal to 1 by Jn omega 0 into Gn, but Gn is minus a by pi. Okay, what is omega 0? We know Ts is equal to 1 by pi. Ts is equal to pi, right? Ts is equal to pi. Therefore, omega 0 equal to 2 pi by Ts, that is equal to 2 pi by pi equal to 2. So omega 0 equal to 2. So I can replace 1 by Jn into 2 into minus a by pi. Okay, but you know 1 by j is equal to minus j. So minus a into minus j divided by 2n pi, which is a j by 2n pi. Okay, aj by 2n pi. So this is the complex exponential Fourier series coefficients of the signal x of t. But you may have to write the trigonometric Fourier series coefficients of x of t. So there is one last relation you need to by heart. It is nothing but the relation between complex Fourier series coefficients and trigonometric Fourier series coefficients. This is very important. The relation is Cn is equal to an by 2 minus jbn by 2. Okay, Cn is equal to an by 2 minus jbn by 2, where an and bn are our Fourier series coefficients, trigonometric Fourier series coefficients, which I have already written the expression in the first. Okay, so we have obtained Cn is equal to aj by 2n pi. All right, by comparing these two equations, you can simply know that there is no real part in Cn for the trigonometric Fourier series, because you can see only complex part. Okay, so an by 2 is 0, that becomes an equal to 0. So simply by observing an equal to 0. And what is bn? You can compare these two terms. These two terms are complex terms. So we can write that a by 2n pi is equal to minus bn by 2. 2 is getting cancelled. That implies your bn is equal to, what is bn? Minus a by n pi. So these are the Fourier series, trigonometric Fourier series coefficients. Our final answer, an equal to 0, bn equal to minus a by n pi. And once you know this, what is the signal? Signal x of t is equal to a0 plus sigma n equal to 1 to infinity an cos n omega 0 t plus sigma n equal to 1 to infinity bn sin n omega 0 t, right? That is equal to a0. We have already calculated a0's values as a by 2 plus sigma n equal to 1 to infinity an cos n omega 0 t. Omega 0 was 2. Omega 0 equal to 2. Okay. And an equal to 0. That means this entire sigma term will end up in 0. Okay. So we have only sigma n equal to 1 to infinity bn sin n omega 0 t. What is bn? Bn is minus a by n pi into sin n omega 0 is 2. So n 2t. Alright. That is equal to a by 2 minus a by pi into a by first I think n equal to 1, so minus a by pi sin 2t. Okay, second term is minus a by 2 pi sin 4t. For n equal to 3, a by 3 pi sin 6t, and it goes on like this. Okay, so this is the final Fourier series, trigonometric Fourier series expression for x of t. Okay, so this, if you know all these expressions or tips, right, these tips, it is very simple. You will take only less than 5 minutes to obtain the answer to this question. So study well all these relations and obtain the output. Okay, the next question is, find the CTFT, continuous term Fourier transform of the signal x of t equal to t e raised to minus at u of t using an appropriate property. State and prove the property used. So this is nothing but differentiation in frequency property. We can make use of differentiation in frequency property. It's a simple question. Okay, we can start from the scratch. What you know is e raised to minus at u of t will be having a Fourier transform 1 by a plus j omega. This is a standard result. You might be knowing that. Okay. Now, what is the Fourier transform of minus j into t e raised to minus at u of t? That's why you have to use the differentiation in frequency property, because it says that if x of t and x of j omega are Fourier transform pairs, then minus j into t into x of t will be having a Fourier transform. This is nothing but d by d omega of x of omega. frequency differentiation property. You are differentiating the frequency domain. So while differentiating the frequency domain, what you will encounter is a multiplication by minus jt in the time domain. Okay, minus jt in the time domain. So what is the Fourier transform of minus jt into e raised to minus at of t? It is nothing but d by d omega of 1 by a plus j omega. Okay, so what is d by d omega of 1 by a plus j omega? It is equal to minus 1 by a plus j omega the whole square into j. Okay, that is minus j by a plus j omega the whole square. So what we got is minus j into t into e raised to minus at u of t will be having a Fourier transform minus j by a plus j omega the whole square. But is this the question? No, the question has only e raised to minus 8, t e raised to minus at u of t, t e raised to minus at u of t. Okay, so a minus j is extra here. As per linearity property, we can bring this minus j to the denominator of this expression. Okay, so therefore finally t e raised to minus at u of t will be having a Fourier transform minus j divided by minus j into a plus j omega the whole square, that is 1 by a plus j omega the whole square. That occurs to be the final answer. Also in the question they have asked to state and prove the property used. So the property is differentiation frequency property, as I've told you, which says that if x of t and x of j omega are Fourier transform pairs, then minus j into t x of t will be having a Fourier transform d by d omega of x of omega. Okay, so let us start with the expression for x of omega. X of omega is equal to integral minus infinity to infinity x of t into e raised to minus j omega t dt. Therefore, what is d by d omega into x of omega? I'm finding the derivative of this expression both LHS and RHS with respect to omega. So integral minus infinity to infinity x of t will be untouched because the derivative is with respect to omega. Okay, into what is the derivative of e raised to minus j omega t? It is minus j into t into e raised to minus j omega t itself. Okay, dt. Fine. Now this is equal to I can write it as integral minus infinity to infinity minus j into t into x of t into e raised to minus j omega t dt. So this expression is similar to minus infinity infinity. Okay, minus infinity infinity some x dash of t into e raised to minus j omega t dt, which is nothing but the Fourier transform of x dash of t. So this expression is the Fourier transform of minus j into t into x of t. Therefore, the property is proved.